Hello everybody, myself Prasant Mukhopadhyay, faculty member Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So in the last class of our power electronics, we have started a new unit of unit 6, that is resonant pulse converter. So basically in the last class we have discussed a basic introduction of this resonant pulse converter. So why resonant conversions, what is the basic class of resonant inverters, so resonant DC-DC converter, series resonant link inverter, quasi-resonant converter, resonant conversions, its advantages and disadvantages. So with this basic idea, actually today we'll discuss in details of this resonant pulse converter as per our say syllabus, that is curriculum. So last class also I have say told you that this resonant pulse converter content, besides the introduction, this series resonant inverter, parallel resonant inverter, zero current switching resonant converters, zero voltage switching resonant converter, two quadrant zero voltage switching resonant converter, and resonant DC link inverters. So with this and with our say last class introductory part of resonant pulse conversion process or resonant pulse converters, so we'll start today's discussions. Basically in this discussion it will we'll try to cover as far as possible within this class, up to what extent we can cover it. So basically we'll say once again the content of these discussions is introductions, classifications, conclusions, and of course the references. So let's see up to what extent we can complete in today's lecture. Okay, so basically as I told you in our earlier discussions also, the resonant inverters are electrical inverter, so based on resonant current oscillations. So it is known as DC to DC converter or DC to AC PWM inverter, and the main function is to reduce switching losses of devices, MOSFET and IGBT. You know, the MOSFET and IGBT are very say switching device where we can use, and but they have certain say demerits. They have some certain switching losses, so that can be overcome with this resonant pulse conversion process. And so to reduce, actually it cannot be completely reduced in any electronic devices. It can be reduced. Okay, so with these introductions we can have classifications of resonant converters, and this can be broadly classified into 8 types, and these are series resonant inverter, parallel resonant inverter, class E resonant converter, class E resonant rectifier, zero voltage or ZVS resonant converters, and zero current switching or ZCS resonant converter, two quadrant zero voltage switching resonant converters, and resonant DC link inverters. So once again I am repeating these classifications. This is a very broad classifications of 8 types: series resonant inverter, parallel resonant inverter, class E resonant converter, class E resonant rectifier, zero voltage switching ZVS resonant converter, and zero current switching ZCS resonant converter, two quadrant ZVS resonant converters, and resonant DC link inverters. So I think you got these classifications, these 8 types of broad classifications of what I told you. So these are the mostly say broad classifications of resonant pulse converters. Now what is the series resonant inverter? So one by one we will try to discuss all these 8 resonant pulse converters, inverters, etc. So first of all, series resonant inverter. Basically it is based on the resonant current oscillations. In the last class we have discussed about the resonant conversion process, and where we have seen this resonant current oscillations we have seen, and this based on this resonant current oscillations, and switching device are placed in the series with load, and thyristors are work as a switching device, work in a switching device. And this type of inverter produces an approximately sinusoidal waveform at a high frequency, and ranging from 200 Hz to 100 kilohertz. Once again, I'm telling you that it is based on the resonant current oscillations, and switching devices are placed in series with a load, and thyristors are working switching as a switching device. This type of inverter produces an approximately sinusoidal waveform at a high frequency ranging from 200 Hz to 100 kilohertz. So this is actually the circuit diagram for the series resonant carbon converters. So this is the circuit diagram. Okay, see, this is the resonant circuit. Okay, so now actually this is resonant circuit. So this is the mode 1 operations, this is mode 2, okay, and this is mode 3. So we're coming in discussion part. So this is the waveform. Okay, so you see, this is for gate 1, that is for this thyristor 1. This is for gate 2, that is for this thyristor 2, and these are the basically say waveform of current, voltage, etc. Okay, so now what is this? So if you go to this, you will get this the mode 1 operations. This is the circuit. This is the circuit. Okay, and this is for mode 2. This is actually this one. Okay, so mode 2, and this is for mode 3. Okay, clear? Mode 3. Actually this one. So this is equivalent circuit, and this is the waveform. Okay, now this is all about this series resonant inverter, and now we'll discuss about parallel resonant inverter. So now we'll parallel resonant inverter, and parallel resonant inverter is a dual of series resonant inverter. So basically current is continuously controlled, and that gives better short circuit protection under fault conditions. Okay, so this is the circuit diagram of the parallel resonant inverter. Clear? And this is the waveform of the parallel resonant inverter. Okay, so in say short, so parallel resonant inverter circuit, basically it is a dual of series resonant inverter, and current is continuously controlled, and it gives the better short circuit protection under fault conditions. So class C resonant converters, next it has low switching losses, yielding a high efficiency of more than 95%, used in low power applications and high frequency electric lamp. This is the circuit diagram of class C resonant inverters. Okay, this is mode 1 operations, circuit diagram for the mode 1 operations, and this is circuit diagram for mode 2 operations. Clear? So and this is the waveform. Okay, so that's about class. Then class E resonant rectifier. So class C resonant rectifier is based on the principle of zero voltage switching. So ZVS, diode is diode turn off at 0 voltage. and a high frequency diode rectifier suffers from disadvantage, and that is switching losses, harmonic content, etc. So this is the class E resonant rectifier circuit. This is for mode 1, and this is for mode 2. Okay, and these are the waveforms of the class E rectifier process, class E resonant rectifier process. Here now actually so this is so far we have discussed this series, parallel, and then class E. So once again I am telling you, the series resonant inverter based on resonant current oscillations, switching devices are placed in series with load. Thyristors are working switching device, and this type of inverter produces an approximate sinusoidal waveform at a high frequency ranging from 200 Hz to 100 kHz. And this is the circuit diagram. This is for mode 1 operations, this is mode 2, and this is mode 3 operations. And this is the waveforms of this series resonant converter. This is a parallel resonant inverter, so this is actually dual of the series resonant inverter, and the current is continuously controlled, and that gives a better short circuit protection under fault conditions. So this is the circuit diagram of parallel resonant inverters, and the waveforms of the parallel resonant inverter is shown here. Okay. Now class E resonant converter. So it has low switching losses, yielding high efficiency of more than 95%, and used in low power application and high frequency electric lamp. Okay, and this is the circuit diagram of class E resonant inverters. So this is its mode 1 operations, and this is for mode 2 operations. If you go to the circuit diagram properly, you will get the mode of operations, and this is the waveforms. Okay. Now class E resonant rectifier. Class E resonant rectifier is based on the principle of zero voltage switching, and the diode turn off at 0 voltage. High frequency diode rectifier suffers from disadvantage that is switching losses, harmonic content, etc. This is actually class E resonant rectifier circuit. This is for mode 1 operations, and this is for mode 2 operations, and these are the waveforms. Okay. Now we'll go for so before going for the zero voltage switching resonant converter, I think if you go through this lectures, and then if you consult your textbook, so you will have a clear idea about this series parallel and class E resonant inverters, rectifiers, etc. And that will help you. So whenever you will work in the practical field, so this will help you to understand the working process of this type of resonant pulse converters. Okay, so now we'll start the zero voltage switching resonant converters. So zero voltage resonant converter turn on and turn off at 0 voltage. So basically name suggests that zero voltage switching resonant converters means switching process means it includes either turn on or turn off process, and as this is known as zero voltage switching resonant converter, so that means its turn on and turn off are say happen, so it will be turned on or turned off at 0 voltage. And output voltage control can be achieved by varying the frequency and operates with a constant off-time control. So this is the zero voltage switching circuit. So this is zero voltage switching circuit. Okay, and these are the zero voltage switching circuits, different modes of operations. This is mode 1, mode 2, mode 3, mode 4, and these are the waveforms. Okay, so we'll discuss in more. As I was discussing about this 0 voltage switching resonant converters, and I told you that why it is called ZBS resonant converter. So basically, since its turn on and turn off are happened at 0 voltage, and output voltage control can be achieved by varying the frequency and operates with constant uptime control. And this is actually ZBS circuit. See, this is ZBS circuit. This is actually the different mode of operations, and at different mode of operations, what will be the circuit functioning. So that is given in different circuits. This is for mode 1 operations. This is for mode 2, this is for mode 3, this is for mode 4, and the corresponding waveforms are shown here. So these are the corresponding waveforms of this ZBS converter circuits. So these 4 modes, so that is mode 1, mode 2, mode 3, and mode 4, and the corresponding the circuit operational circuits, and as well as their waveforms are shown. So this is the voltage and current waveforms. So actually this is actually ZBS. Another one is zero current switching resonant converters. Basically zero current switching resonant converter turn on and turn off at 0 current, like say 0 volt switching resonant converters operates, that is turn on and turn off at 0 voltage. Similarly, 0 current switching resonant converters turn on and turn off at 0 current. So this converter can operate at high range frequency, that is 1 megahertz to 2 megahertz, and this is the circuit. Basically, this is the circuit diagram. Okay, so this is a ZCS circuit, and this is the filter. Okay, so these are the different type of switch. That is, this is switch type circuits, L type, and this is M type. This is actually half wave type. Okay, this is full wave type. So, and these are the different say mode 1, mode 2, etc. Mode 1, mode 2, mode 3, etc. Operational just circuit diagrams are given. These are the waveforms of ZCS resonant converters. Okay, so basically this is about this all about the zero current switching circuit. We are not say discussing very details of this, but we are giving you just outline of this circuit diagrams, this operational process, how it can be, the circuit can be say synthesized or analyzed. So this is the switch type, half wave type, full wave type, different modes, mode 1, mode 2, mode 3, and these are the waveforms, okay, of ZCS. So that's all about say zero current switching. So now we'll talk about 2 quadrant ZBS resonant converters. So in these converters, ZBS concept is extended here. F0 greater than output frequency is greater than Fs. So F0 output frequency is 1 by twice by root LC, and the circuit diagram of 2 quadrant ZBS is like this. This is the circuit diagram of 2 quadrant ZBS. Basically, these are the waveforms. Okay, voltage and that kind of waveforms of 2 quadrant ZBS. Clear? So This is about ZBS, two quadrant types. Here, this is the principle. This is certain type of two quadrant ZBS. This is the waveforms of the two quadrant ZBS. Okay. Then we will come to resonant DC link inverters. So the DC link inverter is similar to the PWM inverters. This is a circuit diagram of a DC link inverter. Clear? Okay. And these are the waveforms. This is the waveform. LK and link and your AB. Okay, so these are the waveform DC link. So from this, what we can conclude. So basically, it is used for high frequency applications, and ZCS and ZBS becomes popular, and they can turn on and turn off at 0 voltage and current respectively, and also eliminate switching losses. And in DC link inverters, resonant circuit is connected between the inverter and the DC supply. Okay. So with this we have we can conclude this discussion. So once again, before going on the conclusions of this discussions, say we have a quick recapitulation of what we have so far discussed. So that is, if we have a quick overview of this. So in today's discussions, actually we have started our discussions with a basic introductory part, which what we have gained in our last class, and then we have extended this discussions process, that is by resonant conversions and how it is being used for different types of resonant converter, pulse converters. So once again I am telling you, this is actually used in electrical resonant inverters, or electrical inverters are based on resonant current oscillations, and it is known as a DC to DC converter or DC to AC PWM inverter. And main function is to reduce switching losses of the devices, that is like MOSFET and IGBT. And these are classified into 8 broad classes: series resonant inverter, parallel resonant inverter, class E resonant converter, class E resonant rectifier, 0 voltage switching ZBS resonant converter, 0 current switching ZCS resonant converter, 2 quadrant 0 voltage switching resonant converters, and resonant DC link inverters. So that will cover the entire content of our this unit. And with this series resonant inverters, basically based on the resonant current oscillations, it is being work. So switching device are parallel in series with load, and thyristors works in switching as a switching device, and this type of inverter produces an approximately sinusoidal waveform at a high frequency ranging from 200 to 100 kilohertz. And this is the basic circuit diagram of the resonant series resonant converters, and these are different modes: mode 1, mode 2, mode 3 operations. That is these are the equivalent circuits of these different modes of operations of this basic series resonant circuit. And these are the waveforms of the corresponding different say parameters, that is current, voltage, etc. And next, parallel resonant inverters. It is a dual of series resonant inverters, and current is continuously being controlled, and that gives better short circuit protection under fault conditions. This is the parallel resonant circuit diagrams and its waveforms. Then we have discussed class E resonant converters. It has low switching losses, yielding a high frequency efficiency of more than 95%, and used in low power application and high frequency electric lamp. So this is actually class E resonant say inverter, and these are the equivalent circuits of the different modes of operation, mode 1 and mode 2, and these are the different waveforms of the parameters, voltage, currents, so the of different voltage and current waveforms. So then class E resonant rectifiers, and this is based on the principles of zero voltage switching, and diode turn off at zero voltage, and high frequency diode rectifiers supposed from distance that is switching losses and harmonic current. And this is class E resonant rectifier circuits. This is the different mode of equivalent circuit of that different mode 1 and mode 2, and these are the waveforms of the class E resonant rectifier. Then we have to discuss zero voltage switching resonant converters. Basically, turn on and turn off process of this type of converters happened at zero voltage, and that's why it is zero voltage switching resonant converters. And output voltage control can be achieved by varying the frequency and operates with a constant uptime control. And this is ZBS circuits. Okay, and this is actually the different mode of operations. Mode 1, mode 2, mode 3, mode 4 of ZBS circuits, and these are the waveforms. Okay. Then also we have discussed zero current switching resonant converters, zero current switching resonant converter, turn on and turn off at zero current, and this converter can operate at a higher range of frequency, that is 1 megahertz to 2 megahertz. This is the circuit. This is the zero current switching circuit part, and this is the filter. Okay, and these are the different mode of types. This is switch type, this is half wave type, this is full wave type, and these are the different modes of operations of this ZCS. Okay, and then this is the waveforms of ZCS. Then we have discussed about the two quadrant ZBS resonant converters. Basically, concept is ZBS concept is extended here. Output frequency is greater than the source frequency, and this is the output frequency, and this is the circuit of ZBS. Okay. Now this is waveforms of the two quadrant ZBS, voltage and current waveforms. Then also we have discussed resonant DC link inverters. So the DC link inverters is similar to the PWM inverters, and this is the circuit diagram of DC link inverter, and this is the output. This is the waveform. Okay, link as well as this output. And what we can conclude is that it is used for a high frequency application, and ZCS and ZBS becomes popular, and they can turn on and turn off at zero voltage and current, and also eliminate switching losses. And in DC link inverters, resonant circuit is connected between the inverter and the DC supply. And we have taken the help of the power electronics by Rasi, then by Bimda. So with this discussions, you will get a breezed concept of this pulse resonant pulse converters, and if you want to know the more details about this, you must follow the different website of this resonant pulse converters, and you can have to go to the text very carefully, and that will help you to know the subject better. So with this, this is all about this resonant pulse converters, and hope you will get some idea about this, and why it is used, why it is used, and how it can be modeled, and how it operates. So this basic idea will help you in your say practical life, that is when you will work with this type of converters in your workplace. Okay, so with this I thank you all for your patient hearing. And if you have any problem, we have already told you that you can contact me later on so that we can discuss about the problem. Thank you.